video we are going to discuss about the equations of motion for viscous damping. If you directly want to check out the equations of motion, you can just skip to the duration that I've mentioned in the description box down below. Before we start about the equation of motion, I would like to tell you guys a few terms which you have to be familiar about. And the first one here is vibration. So what is vibration? Vibration is the motion of a particle or a body having displaced from a position of equilibrium appearing as an oscillation. What does that mean? When a body gets displaced, it tries to get back to its original position, which appears to be in the form of an oscillation, and that is known as vibration. A very good example is when you strike a string that is attached to both the ends, the string vibrates. That is vibration. The vibratory system comprises of a means to store a potential energy, kinetic energy, and a means by which the energy is gradually lost or the energy is dissipated, and that is called as damping. So what is potential energy? The energy stored due to its position relative to zero position. So when a body is displaced, the energy is stored in the form of potential energy, and the energy possessed due to its motion is called as kinetic energy. So there we have potential energy, kinetic energy, and I've already told you what damping is. Damping is the mechanism by which the energy is gradually lost. A fine example could be a swing. The swing slowly comes back to its original position after you push it. And another example could be the string in the guitar. So when you strike, the string vibrates and slowly gets to its original position, and that is called as damping. Now let's talk about translational motion. So we are discussing about the equations of motion, and there are three types of motion: translational, rotational, vibrational. And over here we're talking about translational motion, specifically the motion in a straight line. Example, a bullet being fired from a gun. The motion of the bullet is a straight line. And there are three terms which we must know to describe the equations of motion, which is spring, mass, and damper. It is said that the change in the length of the spring is proportional to the force acting along its length, meaning the force is directly proportional to the length of the spring or the change in length of the spring. So I can write F is proportional to X, and when I remove the proportionality, it becomes F is equal to Kx, or F is equal to Kx minus U, where X minus U is the change in the length of the spring. So K is a proportionality constant, and K is referred to as the spring. The second term is mass. So for an object having a mass m, the acceleration is directly proportional to the force acting on the object. Or we can also describe it in terms of Newton's second law of motion, which is F is equal to ma. Let x be the displacement, and when you differentiate it once, we get velocity, which is x dot, and when we differentiate it again, we get x double dot, which is acceleration. So F is proportional to the acceleration, which is x double dot. When I remove the proportionality, I get F is equal to mx double dot, where m is mass, the proportionality constant. So we have stiffness here, we have mass here. And then for damper, it says the applied force is proportional to the relative velocity of its connection point. Let's say there are two velocity for a system. The relative velocity becomes x dot minus u dot. So they say that the force acting is proportional to the relative velocity, and when I remove the proportionality, it becomes F is equal to C x dot minus u dot. C, where C is the proportionality constant, which is the damper. I can also write it as F is proportional to the velocity, which is F proportional to x dot, and when I remove the proportionality constant, becomes F is equal to C x dot. So we have stiffness, we have mass, and we have the damper. Now talking about springs, springs can be arranged in series or in parallel. When the springs are arranged in a parallel format, the equivalent spring stiffness, Ke, becomes the sum of all the stiffness together, which is K1 plus K2 plus K3 and so on. Equivalent stiffness in series becomes 1 by Ke equals 1 by K1 plus 1 by K2 plus 1 by K3. In a conservative system, the total energy at any instant is constant. So when I don't have any damping, the vibration continues. And when there is damping, the vibration gradually slows down and it goes to rest. So that is the role of a damper. Now let's talk about damping. Damping is a phenomenon in which the energy of the system is gradually reduced, or the amplitude of vibration goes on decreasing, and finally the vibration of system is completely eliminated and the system is brought to rest. Like I already mentioned, the orange graph here represents a system where damping is present. So the energy of the system is gradually decreased, and as you can see, the amplitude also decreases, bringing the system to rest. There are different types of damping, like viscous damping, Coulomb damping, structural damping, and so on. But in this video, we will be discussing about viscous damping because we are concentrating on the equations of motion for viscous damping. Viscous damping results when a system is made to vibrate in a surrounding medium that is under the control of highly viscous fluid. What do you mean by highly viscous fluid? Viscosity is the resistance to flow. So when there is higher resistance, the damping which arises because of such a system is called as viscous damping. Now let me show you an example of a viscous damper. This is also called as a dashpot. As you can see here there's a tube which is filled with a viscous fluid. There's a piston here, so this is a cylinder, there's a piston here, and the piston is surrounded with viscous fluid. This can be noticed in a shock absorber in a vehicle. So what is the role of the shock absorber? So in a shock absorber, there is a viscous damper present, and the piston moves as quickly as the wheel jumps, or as quickly as the wheel moves, the piston also moves, thus offering resistance. So while the vehicle moves over a bumpier surface, it doesn't jump much because of the dashpot present. And this is a very good example of a viscous damper. So basically what a viscous damper does is it absorbs the shock, or it absorbs the jerk which is caused due to uneven surfaces. So this is the role of a damper. Now let's move on to the equations of motion for a viscous damper. Now I hope you all understood what a viscous damper is. So here we have a system with mass m and spring stiffness k, and there is a damper C present, preferably a viscous damper. Like I've mentioned already about the mass, damper, and the stiffness, so we are already familiar with these terms. So the forces acting is mx double dot F is equal to ma, and we have F is equal to cx dot, which is damper into velocity, and we have F is equal to kx, stiffness, into the length. So these are the forces acting, and when I add all these forces, since the system is in equilibrium, so this is the equation of motion. Mx double dot plus cx dot plus kx equals 0, and I'm substituting x as e power lambda t because this is the displacement of a wave. So when I differentiate it once and twice, I get velocity and acceleration. The differentiation of e power 2x is 2 into e power 2x. So based on that, I have lambda e power lambda t here and lambda square e power lambda t. So I have displacement, velocity, and acceleration. So I'm substituting all the given equation. So I have something like this. It's obvious that e power lambda t is common to all the three terms. So I am taking e power lambda t outside and I'm bringing that to the right hand side, so that becomes 0. So the solution, or the equation I am left with, is m lambda square plus c lambda plus k equals 0. The solution for this equation can be written as minus b plus or minus root of b square minus 4ac divided by 2a. So So this is a solution for any equation. And from this I know that A is M, B is C, and C is K. So I have minus B, which is minus C, plus or minus root of B square, which is C square, minus 4AC. 4 into A is M and C is K, so 4KM, divided by 2A, and A is M here. So I have the solution here. And what I'm doing here is I am dividing the equation throughout by M. So this becomes lambda square plus C by M lambda plus K by M equals to 0. Okay? And if I have to write the discriminant for this, which is discriminant is B square minus 4AC. Okay? So that is B square minus 4AC becomes C by M square, which is B square, minus 4 into A is 1 and C is K. So this portion is the discriminant term. And if that is equal to 0, it is called as, the system is called as critically damped system. If the discriminant is positive, it is called as, the system is called as overdamped. And if the discriminant is negative, the system is called as underdamped. So we have overdamped, underdamped, and damped system. So we have found the equations of motion for viscous damping, and we found the solution for it. And using the discriminant term, we can say if the system is overdamped, underdamped, or critically damped. Now let's consider the case where the system is critically damped, meaning the discriminant term equals 0. And I can write C as Cc because it is critically damped. Cc is the coefficient of critical damping. So Cc square by M square minus 4K by M equals 0. I can also write this as Cc square equals 4K by M into M square. Now, the formula for frequency omega n equals root of K by M, and I have K by M there. So K by M is actually omega n square. So substituting this there, I get Cc square equals 4 omega n square M square. So taking square root of that, I get Cc equals 2M into omega n. And the other formula is, I know omega n is equal to root of K by M. So we've already found Cc equals 2M omega n. When I substitute omega n here, I have M and root M. So that becomes 2 root Km. So I have two formulas for Cc, coefficient of critical damping, which can be written as 2M omega n or 2 root Km, which is what is given here. Okay. Now, the ratio of actual damping, which is C, to the critical damping coefficient, which is Cc, is called as the damping ratio divided by P, or it can also be written as ρ, which is equal to C by Cc. When the damping ratio equals to 1, it is called as critically damped system. When it is lesser than 1, it is called as underdamped system, and when it is greater than 1, it is called as overdamped system. Now, I can say C by Cc equals 1 because it's critically damped. So from that I know C equals Cc, and I know that C is equal to 2 root Km. So I am going to substitute that value over here. So I know that C is equal to Cc. So this becomes 2 root Km the whole square, which becomes 4 Km. So this term becomes 0, which I have described here. I know that Cc equals 2 root Km. When I substitute that in place of C, it becomes 4 Km minus 4 Km. So this value becomes 0. So the only root that is left out is minus C by 2M. So the only root alpha equals minus C by 2M. And the general equation becomes, so if there are two roots, this becomes A into e power alpha t plus B into e power beta t. But here we just have one root. So the general solution becomes e power lambda alpha t into a plus beta t. And the value of alpha is minus c by 2m, which is being substituted here. To simplify this equation, I am multiplying and dividing this by cc. So I have c by 2m, forget the negative sign. I have c by 2m here, and I'm multiplying and dividing it by cc. So I have c by 2m, and I can write cc as 2 root km. So it becomes c by 2m into 2 root km by cc, and c by cc becomes p, and what is left out is 2 root km by 2m. And the 2 and 2 gets cancelled, so I'm left with root km by m, and root m by m becomes 1 by root m. So this actually becomes p into, 2 and 2 gets cancelled out, so this becomes p into root of k by m. I think I've mentioned that somewhere. Okay, the beginning. Okay, there you go. So c by cc is p, and 2 and 2 gets cancelled. 2 root km by m becomes root of k by m. So this is p root k by m, and I know that root of k by m is omega n. So this becomes p omega n. So that's how we got p omega n. So I can substitute this in place of c by 2m. So the equation becomes e power minus p omega nt into a plus pt. So this is the equation of motion for a critically damped system. Now let's move on to the case where the equation of motion for overdamped system. Equation of motion for an overdamped system, the discriminant is said to be positive. So I know both roots are real and distinct. That is, yeah, these are the roots, and I know both the roots are real and distinct. So that is, alpha is minus c by 2m plus or minus root of c square by 4m square minus km. So what I'm doing here is I'm multiplying and dividing throughout by omega n. Okay, and I'm taking omega n outside. So this becomes minus c by 2m omega n plus or minus, so this is omega n square, so that when it comes outside the root it becomes omega n. So that is what we have here. So this becomes c square by 4m square omega n square minus k, same thing, divided by m omega n square. I can write 2m omega n as cc. We know this equation from the previous steps. So I'm substituting the formula of 2m omega n as cc here. So this becomes cc square, because it's 4m square omega n square, so that becomes cc square. And again I have 2m omega n here, so this becomes omega n into minus c by cc plus c square divided by cc square. And over here we have k divided by m omega n square. Okay, and I can write k by m as, this is k by n as omega n square, root of k by m is omega n, so k by m is omega n square. So I have omega n square by omega n square, so this term becomes 1. So that's how we got omega n into minus c by cc plus or minus root of c square by cc square minus 1. And I can write c by cc as p. So this becomes omega n into minus c by cc is p, so minus p plus or minus, this is p square, so I have p square minus 1 here. So the roots are omega n into minus p plus or minus root of p square minus 1. So the general solution for an overdamped system is a, like I said, when you have two terms, you have a e power alpha t plus b e power beta t. So I'll substitute alpha and beta here. The only difference is alpha is omega n minus p plus root of p square minus 1, and beta is omega n minus p minus root p square minus 1, which is what we have here. So this is the general solution for an overdamped system, and this is a solution for critically damped system. For underdamped system, we'll be discussing that. So if you guys have any queries or suggestions, you can comment it down below, or you can write to us in the email ID provided in the description. And if you also want us to do a video on a specific topic, you can also write that down to the email provided. So thank you. I hope you all understood.